No, but they're not. We're not competition.
So, hey everybody, thanks for coming out to the Atlanta Monthly Robotics Meetup. We are happy to be here at the Georgia Tech RoboJackets facility, and RoboJackets is our host. Big round of applause for them for doing this. Thank you. In a second, I'm going to introduce the president of the GT RoboJackets, and he'll tell you a little bit more about the work that he does and the teams that compete. I believe there are how many? 4 or 5?
4 competitive teams and 1 outreach.
4 competitive teams and 1 outreach team. We'll hear a little bit more about that. They've been real gracious with their time. So in a second, I'm going to turn it over to Jason. I just want to make some quick announcements. Let's see, next month's meetup is cooler than this one. Just kidding. We actually have the guys from OSRF, which is the guys behind Ross. If you have worked with the robotic operating system, they are coming to give a talk. It's going to be a signature event, so we're pretty excited about that. That one will probably be at the Atlanta Tech Village, a little bigger space, and we're excited about that. So, without further ado, I do want to turn it over to Jason. Jason, you have the floor. Thank you.
Hey guys, so I'm just going to kind of give a brief presentation. So I'm just going to talk about RoboJackets and kind of what we do, our different projects, and then I'll talk about the teams we do, and then we'll have a tour, and there's some guys here that want to talk about what they do more specifically in more detail, so we'll do that. I'll just kick off with the best video of all time.
Oh, this is a good video.
This is just kind of high level, a lot of the stuff we do.
Pretty hype.
Okay. There we go. All right. So RoboJack was kind of founded 20 years ago at this point. We're actually hosting a 20th anniversary competition coming up. So back in 1999, a bunch of college students got together for essentially a senior design project, decided they were going to build a robot. That's what they made. RoboBots right there. Tank drive, 4-sided, essentially push bot. So they went to competition and they got destroyed. As any great organization's starting point, that is where we began. So then things continued, and we kind of started adding on more parts of our organization and kind of built this mission statement around education, advancement, and promotion in the field of robotics. So it's not just building the robots, it's more than that. It's going out to schools and talking to kids about STEM and robotics and everything that they can do with this. So this is one of our events we host. So we do this event called Kickoff every year. We have about 1,000 high school students come down to the First Center at Georgia Tech. We give presentations on what RoboJackets does, what IRIM does, the Institute of Robotics and Intelligent Machines on campus. So their director comes down, and essentially reveal the game to them that year, so they know what they'll be building for. So we host that every year. We also volunteer. We send about 30 to 40 people across volunteering across around the whole year. We do about 4,000 hours of volunteering across the entire organization. So not only do we build robots, we support competitions in the local area that we need to so they can exist. So we also train our members. So educate. People come into Georgia Tech and they're like, I want to build robots. That's super cool. I don't know how. Can you teach me? And the answer from RoboJackets is, of course. We expect no prior knowledge. Students come in and they're like, hey, let's get started on some things. And it's like, okay, over there, I'll show you how to build a ROS. I'll show you how to start your first node. So that's kind of what we spend a lot of time doing in the fall. And you see a couple of things that they're doing. So not only are we talking about building robots, they're actually doing it. They're programming on real things and seeing that if I set the motor powers to be the same, it doesn't drive straight. And those important skills of like, hardware is hard. They also do some soldering, they do some PCB development, they do some mechanical design. So more than that, we do soft skills. Engineers, you may not know this, are bad at communicating with non-engineers. I know, shocker. Also bad at communicating with engineers of different disciplines. Now, robotics, multidisciplinary. I have a software guy who's never touched CAD or a machine in his life, talking to a mechanical guy saying, I need it to be here. Put it here. So they learn how to do that and those kind of skills, and how to do leadership and all of that, how to lead a technical project. So kind of break down by major, we're about a third ME, about a third CS, about a third EE Comp E. AEs sprinkled in there. They kind of count as MEs, sort of. Then we have a couple of others. So a lot of people come in and do things different than their own major. We have a lot of MEs doing CS, and we have CS majors doing ME, or at least trying to. So we also advance. We build lots of robots. This is just a couple of the robots we built last year, and some ones that are kind of counted as this year as well. So we take this around the world. So we go to competitions all across the world. These are just some of the places that we've gone to competition over 20 years. And in fact, one person went on so far to say that RoboJackets was more important than their entire PhD, which I say he got a master's, so I continue doing RoboJackets, so far I'm on track. So budget, we do about 125 to 130K a year, entire budget. This just kind of comes, this is kind of breakdown by team. So RoboCup is so large, BattleBots is so large because of travel for the most part. Actual cost of building the robots is not equal, but more equal. So funding sources, we get a lot from sponsors. We get a lot from SGA, so our student government actually supports us by giving us like 70K a year, which is really nice. We also get dues mandated by them. We get some money from the Institute, a lot of support from the Institute. This does not count the space that we're currently in that we get access to 24/7, which is really hard to calculate in the middle of Atlanta with a nice machine shop and what that looks like. So an amazing support across the Institute, and we're always so thankful for that. So getting into the teams, we do outreach. I like to go out to schools and talk to kids about robotics and how they can get more involved in robotics and go to competitions and volunteer and judge and just get very involved in what's going on, and so do the rest of our members. So really just kind of giving back. We have a whole team centered around that. They're actually the ones doing mentorship right now, which is when you see our shop, it's all chaos and there's stuff everywhere. That is because the team that we help, Wildcat 5E, 705, is an FRC team, and FRC, the last day they can build the robot is today at midnight. So you're gonna see a little bit of that tonight. Yeah, it's gonna be a fun time. So we do our first team. The first team that we started with is BattleBots. So just like you'd expect on a TV show, 2 robots, gladiatorial style combat. Whoever gets knocked out first loses. So we compete in multiple different weight classes. Starting off, we have, these are the bigger bots. We do 30-pound ring spinner. So this is Kathy. Kathy was built last year. We were essentially told that you could not do a ring spinner at 30 pounds. It was not effective. When you have a perfect ring and you spin it, and you get hit really hard, it tends not to be a ring, and then it's really hard to spin. So we were like, oh, we're at Georgia Tech, we can do that. So we did. After like 4 years, which is really amazing about these BattleBots. Some of them are which I'll get to in a second, have been built for so long that the students who started the project are very far graduated. So specifically, Mandy right here, our 120-pound drum spinner, was started back in 2010. So we essentially had 3 generations of students that I have not met that have worked on her, including one VJ right there, who's sophomore, right?
Yeah.
So he's essentially working on a robot that was started 10 years ago. He's never met the people that initially designed it, but they have little notes of what went wrong, and he's been working off of that.
And he'll leave notes for the next 10.
Yeah.
Is that what that thing is?
Yes, so this is actually Mandy partially assembled. She's like in the middle of her build process. So she's a giant drum spinner. Drums super heavy, spins super fast, and hits really hard. There's some good videos on YouTube if you're curious. So this new sumo. So this autonomous sumo, it's like what you'd expect from a sumo competition in real life, except with robots. So it's cooler. This is a 3 kilogram weight class, so you are allowed to have up to 3 kilograms at most. But you're on a steel floor, so you can put magnets on your robot. So the effective weight of this robot is about 150 pounds, and the next generation will be about 300 pounds, which is super exciting. It also moves like multiple meters per second in a ring that's like a meter by a meter, like a ring of a meter. So things are moving super fast. It's all autonomous. It's super terrifying, and it's a lot of fun. So IGVC, this is kind of my home team where I got my start. So we essentially build the robot on the right that navigates the course on the left. I know nothing about the course before I start, other than the fact that there will be obstacles on the course. It will probably be outside, and it'll probably be raining, just because that's how competition goes every year. So essentially they give me GPS waypoints, they say drive here, and they need to figure out the obstacle course as you go. So figuring out where the obstacles are and avoiding them as such. So this is us at judging. There's me super happy with the robot. And here's the video of what that looks like. So essentially it's using a camera up top, right there, to detect these white lines, and there's a LiDAR right there, which is used to detect these barrels. And it combines all that into a map, then does localization to actually do global mapping, and then global planning, and then path following on top of the path planning. So it's a fun robot. Very heavy. It's about 300 pounds, you can sit on it, that kind of stuff. So this is just some beautiful shots of what that robot looks like. I'm super proud of it, so yeah. So we also do all of our own electrical stack. Every robot you've seen here was designed and built by undergraduate students. So from the mechanical, electrical, to software side. So not only do we make our own robots, like physically machine them, we also write our own firmware, write our own software on top of that. The autonomous teams will use ROS, RoboCup uses its own stack, but we'll get there. So on the software side, we use ROS, big surprise, super useful. OpenCV, Gazebo, all the things you would see kind of in industry. RoboCup. So RoboCup is a conference centered around having robots beat the World Cup champions in full-on soccer by 2050. So humanoid robots, world champions, you can't do anything while they're playing. So essentially how this competition works is you have 6 robots. We're kind of focused more on the strategy side. So smaller robots without weak legs, because all legs make is a hard controls problem. You fall over a lot, and they essentially do full-on soccer. So you put the ball down, you put the robots down, and they figure out everything else. You just kind of get to watch. That's kind of what this looks like. So you'll see on top there's these dot patterns. So there's an overhead camera that's reading that dot pattern to figure out where the robots are and relaying that information back to us. There's a delay though, so you actually have sensor fuse in between. That's one of the things we're working on right now. Where are the white lines? That's not very clear.
Come on, white team.
Yeah.
You can do
So we
it.
have a full holonomic drive with those wheels, so you can move in any direction. We have a kicker right in the middle, which is essentially a bar that shoots out through a solenoid and kicks the ball. You can kick it much faster than realistically. So they kick like 10 meters per second, which the league has been cutting back on that to make it more close to soccer.
Yes.
Yeah. So, there's a lot of good things about that. So those are actually your wheels right there, and you can see how there's little rollers on them, which means you can spin in any direction. So essentially XY translation and theta are independent of each other. So that is our dribbler. So what that does is it's a piece of foam that spins really fast. So it gives backspin on the ball, so you can actually keep control of the ball as you're moving around. That's the kicker right there. It's kind of hard to see. and that just shoots out really fast and kicks the ball really hard. So we do all-around electrical PCB development, so the stuff you've seen developed over the last essentially 10 years. I think we just did version 3.1. Sound right? Design review. So essentially broken down to two. You have control, which does the actual microcontrollers, doing the onboard control. This is an FPGA. And then we have kicker board, which is just a bunch of capacitors and discharging them so that you can actually kick. So mechanical, same thing. This is actually cat of the dribbler, so it looks like. So this essentially centers the ball so that when you kick, it shoots forward instead of off to the side. On the software side, everything is pretty nested. They essentially have a strategy. They have a hover little strategy. They have essentially like a play system for that. So where global robot strategy should be, they have each individual robot has a thing it is doing, and then everything it's made of is made up of like specific motions. So this is the competition that goes all around the world. They compete internationally every year. Last year was Canada. The year before was Japan. This year will be Australia. So we meet lots of people from different countries. It's a lot of fun. So RoboRacing is our newest team, and they essentially build two robots. They build a small robot on the right, which is called Sadani, and they build a robot on the left called the goalie. There's a pasta theme. They can talk more about it. There's a fun fact about some of these. So this is kind of what the goalie looks like. So what's fun about that competition is you're sitting in this car. As you saw, there was no steering wheel, so the car is driving autonomously, like 10 miles per hour, which is. It sounds cooler as 10.
Meters per second, yeah, it's raw.
So they're driving really fast, and you have tasks to do as you're driving around, like shooting targets and holding a cup of water. And I've been told it's very terrifying. Is that right, Joe?
Yes. That's me.
Yeah.
You have to trust your team.
Essentially, you do an autonomous stopping here, which is what you're typing right here. So it sees that red line that was passed. What's funny is this car actually didn't have brakes when this happened, so it just happened to stop right before the line.
We drove the motor backwards.
Oh, you did? Never mind.
Power stopped.
So they compete in an autonomous competition up in Colorado called Spark Fun. Also, we send some BattleBots there. And then there's also IRC, which is a small robot, but more like line-based navigation in a parking lot, which is what this is like. Right now, they're actually training a neural network, which Evan will talk about maybe. I don't know if that's your or not.
I actually didn't put that in the network.
Okay.
Like, you can talk to me about it afterwards if you want more.
If you want to know more about our end-to-end network, you can talk to Evan. This is them training that right now.
It's the same thing as the DIY RoboCars presentation last month.
Okay, that's cool. As we do, again, software ROS Ubuntu. That's essentially, we run everything on Ubuntu. RoboCup does not use ROS since they were kind of started before ROS was big and have not switched over ever and plan not to. So I will get out of the way and let some people, other people than me talk about some of the more fun projects they're doing. You want to go first, EJ?
Sure.
So this is VJ. He's sophomore on BattleBots. He's a Mandy, right?
Yes. So I'm one of two leads on Mandy. So Mandy, as you can see here, is our 120 pounders, the biggest bot we make. It's a middleweight. She's terrifying, as you'll see in the next video. So this is our fourth iteration of Mandy, fourth major redesign since 2012. Before this, I think there was a bot named Sophie, which this is based on. So last year we actually placed second in RoboGames, which is the best we've ever done.
Awesome.
And if you want to see a bit of what Mandy looks like while she's fighting. So bear in mind, both of these robots are 120 pounds. So when you see them go flying, you just really get a gauge for just how powerful their weapons are. This was Mandy's first fight of the competition, so she was still in pretty good shape when this happened. She wasn't driving so great near the end. We had a couple of pretty rough fights. But yeah, we actually managed to get them stuck in the wall that time.
Yeah. Hot dogging it.
Oh yeah. So, fun part, so because the drum in the front is basically a giant gyroscope, we can do some gyro dancing as you saw there. If you might have seen that the belt shot out while he was doing that. So yeah, let me see. If you look closely, you'll see like that's why we lost. The weapon stopped spinning after a while. So we had another belt on deck. It was fine, but we like to avoid that if at all possible. So basically, I'm leading the next major to redesign since version 3.5, which was last year. So we're generally keeping it mostly the same. You might see some minor differences. For example, we're getting rid of those aluminum side plates right there. The initial justification for those was that they would dissipate energy. However, they would just get ripped off, and I mean, they did dissipate energy. It's just that they didn't justify their weight. In the meantime, we're maintaining this HTP armor we have, which is right here, which actually does very well with sustaining hits. If you can see that was a direct hit from a weapon right there, which scratched it less than half an inch. So these are some pretty sturdy armor.
You said HDPE?
Yeah. So high
density polyethylene.
Yeah. So this is actually what sets us apart from a lot of This sets us apart from a lot of other heavyweight bots because most of them don't actually think to use HDPE. Most of them just focus solely on having a real sturdy chassis, which ultimately is their downfall a lot because, I mean, if you hit this directly, it's gonna bend. So it's nice to have that damping there. And the other major change that we have is that we completely redesigned our drum. So during that last fight, by the end of it, well, let me get to the next slide. Okay. So our drum is completely different from last year. For reference, this is our drum. If anyone wants, this is about 15 pounds of S7 tool steel, and we have 2 of these. If you would like to pass that around, careful. So we have, the drum itself is...
It's a lot heavier than
Yeah.
it looks.
The drum itself is about 30 pounds altogether. And
I'm
we
about to
spin
smash
that
my hand.
at around 8,000 RPM?
Yeah,
It's terrifying. It can, I don't want to be in the arena with that. So the problem is though that last year we had the 2 drum pieces secured with these dowel pins right here. So they were steel dowel pins, and the thing is that little pieces of steel, while steel is strong, but we're taking pretty severe forces, as you can see from here. This is the shaft of that drum rode on,
nice.
and if you'll notice, it's not exactly straight anymore. So this is more than an inch of steel, and something that can bend that is something that we need to prepare against. So we actually did some calculations on this, and we found that in order for it to have bent that much, we needed to take a load of 50,000 pounds. So that was one of the biggest hits we took all competition, and as a result of that, our dowel pins snapped. So we only had half a drum for our last fight, which is less than ideal so we were about 30 pounds down for that last fight, so we took a pretty hard beating. Came in second though, so worked out. But in the end, we decided that we needed a better way to secure the 2 drums together. So ultimately, we decided to, instead of using just a bunch of small steel dowel pins, that we'd incorporate the secure mechanism along with our pulley right there. So rather than using a bunch of small steel pins, we now have this aluminum pulley that slots in with this spline pattern right here. So we did some math, a lot of math to figure out. So based on the number we got from that, we found that we did some shear calculations to find that this would be significantly stronger despite it being made of aluminum. Fun fact, this alloy of aluminum that we're using, 7075, we found out the hard way that it's harder than steel. Because we were cutting through that 3-inch block for about 3 hours on the bandsaw. Yeah, I mean, we knew it was stronger than steel, which is why we knew it was stronger than aluminum, which is why we were using it, but we didn't know just how much stronger. So that was a fun few meetings. Altogether, I think it was 3 hours one night and then 2 hours another, just sitting and watching the bandsaw. So that was a fun time. So, but we're going to be machining that on the Haas, and that will then slot in, and the 2 drum halves will be slotted into that. And the math seems to say that it'll hold together, but we're going to be doing some, we actually have the chance to do some actual testing this time to see whether or not our math holds up. And in addition to that, we've also made our shaft significantly thicker so that that doesn't happen. Yeah, so all in all, our bot hasn't changed very much because we got second last year. We're at a point where our design has been pretty refined, so that we're just making a few finishing touches to just get this as refined as we can.
How will you place next year?
So competition about that. Oh man.
Uh-oh.
Loaded question.
Yeah, it is. The person that runs competition has decided to move to France, and so there is no more competition for this. So right now, Mandy's being built as a glorified paperweight. This, however, does give us a unique opportunity to do some actual testing on this, because like no one has done research on BattleBots, and we would like to know how to actually how to do real math with these things, because no one knows how do you determine how hard you're getting hit, how do you figure out how fast your spin up time is, because these are systems that not many people use. It's a very niche field, so and no one's done research in it before. So we're actually in an interesting spot right now.
So you guys are gonna put telemetry in it?
See, the drive system for these isn't actually that complicated. These are controlled with basically glorified RC card systems.
Mm-hmm.
So there's not much programming involved in any of this except for setting up the transmitters. So BattleBots is primarily just focused on the mechanical side of things, which is unfortunate because we have had in the past a lot of electrical fires. We're gradually improving on that front. We have a lot of Compy students this year, and we actually have a robust electrical program now. So we're gonna see if we hold up.
Thank you.
Next is Varun, who is the project manager of RoboRacing. So, Speedy Boys, as he calls them.
All right, hi everyone. I'm Varun, and I'm in charge of RoboRacing. As you saw earlier, RoboRacing builds 2 robots, and our overall focus of our sub-team is on how to make our robots drive as fast as possible without hitting anything. So on the left, we have our RC car scale robot called Sedani. Sedani is a 1/6 scale RC car that has been converted into an autonomous driving robot. You can see right here is Macaroni. Macaroni is the previous version of our RC car scale robot series. We found a lot of problems with Macaroni in terms of its reliability, its drive system, and its electrical system, so we decided to upgrade our chassis, give us more space to work with, and create something that's quicker and more robust. Thus we came on Sedani. On the right-hand side, you see Big Oli. Big Oli is our go-kart-sized autonomous car that we've been building for about 2 years. Big Oli is styled as the Ramblin' Wreck, which is the Georgia Tech mascot, and you can see we even got RoboBuzz to ride in Big Oli. So I'm going to be focusing mostly on our Sedani developments because that's what we've been focusing on a lot lately as a team. Sedani competes at the International Autonomous Robot Racing Competition, which is held in Toronto, Canada. And that competition requires the robots to race 1 lap around a track, as you can see on the right. The track is is on an asphalt surface and has lines made out of tape that the robot needs to stay between. On the left, you can actually see a robot's point of view. This is from Sedani's front-facing camera, which we use for navigation and obstacle detection. So the overall design of Sedani involves basically 2 sort of major subsystems. We have our computing system and we have our chassis. So our computing system is where all of the software runs and where all of our perception code and autonomous path planning happens. So that all runs on an Intel NUC, for which we have a hot swappable power system, a Blackfly camera, which is a machine vision focused camera, an RP LiDAR, and an inertial measurement unit. And all of those sensors that we take in are allowing us to make educated decisions about how the robot will go forward. And Evan will talk to you guys more about that later. Meanwhile, the chassis module is where we do our actual driving. We've got a control board which we custom designed that uses a microcontroller to interface with all of the pre-existing RC car hardware as well as some extra sensors that we add on. And one of the major things that we focus on is the safety, not only because it's required for the competition, but because we want to keep our robots and the people working with them safe. So we have wireless and a button e-stop system that allows the robot to cut off in the event of any emergencies. So first thing I want to talk about is the Sedani control board. That's on the left is a render of it right before we send it out for production. And on the right is a bit of a schematic about our e-stop subsystem. So the Sedani control board is based around the Arduino Pro Micro. In this case, we opted to actually put on headers so we can slot the microcontroller in and pull it out because we want to be able to switch it out if we want to program on it separately. So we can actually have two different versions of our code running if we want to switch out and test real quick. And it basically intercepts the signals coming from an RC car remote and reads them in. And this is important because one of our major focuses on our team is on deep learning and machine learning. And so for that, we want to collect as much data about the car as possible. One of our previous approaches to driving was using an end-to-end neural network. So a human driver will drive the car around the track and it'll collect data about what the human's driving patterns are and then use those to train a neural network so we can eventually have the car try to mimic that human activity. So basically the conclusion of that is we're very data focused. So the Sedani control board is meant to collect a lot of data and send out the exact signals that we need in order to make the car drive. For that we have a lot of different components. We've got output pins that run out to all of the servos and motors that are on our car, as well as a multiplexer system which allows us to switch between manual driving and autonomous driving. So in manual driving, the microcontroller is able to watch what the car is doing but not have any influence, but then in autonomous we let the controller take over. So one of our major focuses this year was on the LiDAR board to use Garmin LiDAR lights. So on the right you can actually see our board which we have just gotten manufactured. So this is just a screenshot of what it looks like in CAD. And as far as the LiDAR lights go, we wanted a cheaper alternative to the actual RP LiDAR, which we can put maybe back-facing or side-facing to cover our blind spots. And these LiDAR's sensors communicate through I2C and all have the same address when they come from the factory. And you can change the address, but once you've changed the address, if you turn off the robot and turn it back on, it loses that information. So we needed a way to selectively enable and change the addresses of each of our sensors before we could communicate with them further. And that's what this PCB is for. So this was a bit of an adventure in that we also wanted to try a new method of communication, which is Ethernet. So on this board, we actually have the ability to talk over Ethernet to basically a network. So we can put a switch on the robot, have an Ethernet cord plugged into our Intel NUC, and then communicate with this through our TCP system. So in order to make this board fit on either one of our cars, we had to shrink it down really small, which is why we're using, instead of a microcontroller that we can buy separately and put on, we decided to make the board completely embedded. We have an ATmega 32U4 processor on it, and that communicates with all of our LiDARs as well as with SPI through to the Ethernet module, which sits on top of it. And finally, who doesn't like pretty lights? We've got a NeoPixel board that we have in development, meant to light up Bigoli so that when you look at it, you are blinded. And this was a bit of an adventure in power distribution, considering that the amount of lights it takes to brightly light up the entire perimeter of our autonomous go-kart. We draw about 10 amps, so I'm trying to run all of that through a PCB. You can see how thick we've had to make the traces in order to keep this thing from setting itself on fire. But this is, considering that this is also going to be going on Bigoli, we've opted to use the Ethernet interface on that as well, with the ultimate goal of all of our devices on the car being individual modules that we can swap out and easily add in or subtract. And make the car a bit more robust than our previous communication protocols that we've been using. So yeah, that's it for me. I'll pass it on to Evan to talk about RoboRacing software.
How do I pull the presentation, Jason?
Yeah, there's just been the next tab. Escape.
All right, cool. So I made this a little too long, so I'm going to kind of fly through it a little bit and skip some parts. Right, so Varun already talked about IRRC. Our next competition is in July for that. So there are a couple different events at International Autonomous Robot Racing Competition that the software team has to worry about. One of them is the drag race, going in a straight line as fast as possible, which is more tricky than it sounds because there can be bumps and stuff, the car can drift off to the side. Controlling that autonomously can be pretty difficult. There's the circuit race, you just stay between the lines, do one lap as fast as you can. We have obstacle avoidance, which is on the drag race track, but they put cones in the middle, so it's a little bit more like IGVC where we have to identify the cones, plan a path around it, etc. And new this year, there's the urban challenge, where we have this grid of streets, you drive on the right side without crossing the lines, and when you come to intersections, there will be little signs which tell you which way your car is supposed to go in order to get to the finish line, and you have to follow those in order to finish. So that's been a lot of added software challenges for this year, trying to work on that stuff. So yeah, our core problem areas that we work on for our software team are tracking the boundaries of the track with our camera, detecting obstacles and various signals, and real-time obstacle avoidance and planning. We use ROS and all of the tools that come with that, like OpenCV, Gazebo, Point Cloud Library, that kind of stuff. And we also use TensorFlow and Keras for some of our machine learning stuff. All right, so I'm going to tell you about some of the things that we've been working on with boundary detection. So our first pass at this, the strategy that we've used in the past, has been just color detection. So we take an image in from the camera, you convert it to the HSV or HLS color spaces, which you can see an example of this in the bottom. Instead of representing it as red, green, and blue components, you can represent it as something that's a little bit more related to what the color is itself. And this is very useful for it's just about good enough where you can pick out, okay, here's a white line and it's different from the gray road and stuff. In ideal lighting conditions, this works great. But if there are kind of edge cases, in this frame where this is from the car's point of view looking out towards the road, and the sun is low on the horizon and reflecting off the road, and so just based on the saturation and lightness of what we're seeing, it's identifying the things right in front of the road, the road right in front of the robot as being a line. So that's not very good. And so we've been working for a couple years, honestly, to try to fix this problem. So one category of our solutions for these I'd call doing the real computer vision stuff, traditional computer vision. So we want to reduce the sensitivity to lighting conditions. And so we've tried various different methods to do this, some based on edge detection, some based on histogram matching, so taking sections of the image and comparing that versus, so looking at the distributions of colors instead of the colors of single pixels. And we've also tried doing adaptive binarization and adaptive thresholding and that kind of stuff. The best results we've got from all of this over the last 2 or 3 years have been by combining edge detection, which gets very few false negatives, with adaptive binarization, which gets very few false positives. And so that's what this looks like. Just edge detection is on the left, and on the right is all the information fused together into one detection image. So we just got this working this well 2 weeks ago, something like that. So this is all in active development. And yeah, it's going pretty well. A third and totally separate approach from the other ones is using a neural network to do the same task. So the idea is using collected data, learn to label lines in an image. So in the literature, if you want to read more about this, it's usually called semantic segmentation or pixel-wise prediction on images. So the input data might be something on the left. Those are that'll be grayscale image values, right? So there's a line of brighter pixels on the side and darker pixels here, right? And so the labels would be categories. So okay, this is category 0 or background. These are category 1 foreground. These are category 0 background. right? And the neural network will output like probabilities, like how much does it think each pixel is part of the background, or whether it's a line. In case you're fluent in Keras for some reason, here's our network architecture. If you're not, you can look up this stuff, I guess. I'm going to skip over this because we're a little bit low on time. And these slides will all be posted, right?
We can post.
Okay. Well, plus all of our code's up on GitHub, so steal everything you want.
Pull requests
So,
off as well.
Yeah. Fork it, make a pull request, whatever you want. Yeah, so we labeled about 130 images, trained our neural network on this. And like on each of those images, we made random changes to them. So like making it really bright or really dark or shifting the hue slightly. That's something that's called data augmentation. And with this, if you count in each image the number of pixels that we predict right versus wrong, it's about 99%, but that 1% is significant. And so like, here's an example of what the output of that might look like. It gets the whole line on the right, and most of the line on the left, but like here, and misses like just a little bit of the line over here. That would be that 1%. The results we've got from the neural network and from our best traditional computer vision techniques are about the same, and we're maintaining both of them going forward. We'll see which one works better at this year's competition. Right, clicker. Yeah, how are we doing on time?
It's like 8:08.
Should we do the tour?
It's up to them, really.
I don't
We
know.
can keep talking, or we can go to tours with you guys.
Did everybody finish? Everybody get a chat?
I've got like 3 or 4 more slides.
You just finished.
Yeah, okay, I'll speed through these. Let's see. In addition, the robot has to start itself at this competition, right? So there's a light that flips from red to green. We have an algorithm for this that's basically like, maintain a buffer of past frames, and if the oldest frame had red just above where the newest frame has green, then that's our go signal. And that works pretty well. We have cone position detection used for the drag race and for the obstacle avoidance challenge. First, we just use HSV color matching to pick out where the cones are, and then we use a pinhole projection model of our camera to figure out where that is in like real space, I guess, like X, Y, and Z relative to the robot. Yeah, and then finally, we've been working just recently on this like arrow sign detection, categorizing whether or not each of the signs we see is a left, right, or straight. It'll be very important for us to do this accurately at our competition, because if we choose the wrong way or we miss the sign, then we're not going to be able to count our score for the run. So yeah, we look at the image. We look for things that look approximately like arrows in any direction, and then we like zoom in on each of those and do template matching to figure out whether or not it's left, right, or forward. So yeah, if you want to check out all of our code, we're on GitHub. IRC information's up there, and yeah, thanks for your time.
I don't have any other presentations. Essentially, what I thought we'd do is essentially split up into 2 groups, just so you guys fit in all the tight spaces that we have. And then, so Joe can lead one group. Congratulations, you've been nominated to lead a group. So you go Joe, you go with me, up to you guys, just kind of split relatively evenly. That's really all we have for presentation-wise.
All right. All right, we're going on a tour.